Hello and welcome to another video. In this video we're going to be working on sum of distances in tree. And this problem, you have a tree, and so you have an n-ary tree pretty much, where each node can have unlimited children. But for every tree, if you have n nodes, you're always going to have n-1 edges. That's going to make a valid tree, and everything's connected. Those are like the two properties of a tree. So no cycles, everything's connected, and yeah, and n-1 edges. And so your task is to determine the distance from every node to every other node, or to total. So like for this, we want to know the distance from this node to every other node and get a sum of that. So from 0 to 1, this is distance 1, this is distance 1, this is distance 2, this is distance 2, and this is distance 2. So from 0 to every other node, you have 8. From 1 to every other node, you have 12. And then from 2, for example, so this is like 1, 1, 1, 1, so 4, and then 2, so 6, or 6. And then from 3, it's 1, 2, 3 to this one, 1, 2 to this one, so 5, 6, and then 2 to the rest, so 10. These are all the same. And that's basically it. And then there are 10 to the 4th nodes. So essentially you're looking for a linear or like some kind of n log n solution. And so you can figure out the distance from every node to one node. Like let's say I wanted just like, okay, what's the distance from every node to 0? I can do that in linear time just by like looping down, and then anytime I go to a new node, I can just like record how far it is away from here. And then I can do that in linear time. But the main thing to recognize for this problem is like the recurrence relation of like, if I know that, like if I know this is 8, and instead I go here, what changes? Or I go here. So basically what happens is, this is a lot clearer if you just have like a line. So let's say you have a line with a bunch of like things, and you are over here. And the distance from here is something, you know, like it's kind of the same thing. So like, what's the distance from this point to everything else? So you can recognize that if this point moves, right? Like if this point is, you know, let's say it starts here. You have some distance to everything. If it moves, it gets closer to all of these, and it gets farther from all of these. So as you move, you get closer to some stuff, and you get farther from other stuff. And like once we go past this point, now we get closer to less things and farther, you know, like changes how many things we get closer and farther to. So if we keep going now, we only get closer to 2 things, and we get farther from this, and so on. And that's kind of the same thing in the tree. So notice if you move, like let's say we have some number here. Like if we move from 0 to 2, all of these things, 0 and 1, get further away, and all of these things get closer. And so if we have a count of them and a distance from here, we can actually figure that out. So like this total distance is 8. So as we go from here to here, if we just know how many nodes are in each section, like if we know we move from here to here, like we essentially move to a subtree of our tree, right? If we know how many nodes are in here, like this whole subtree, then those nodes all get closer by 1. So if they get closer by 1, we would subtract 4 here, right? Because 4 nodes get closer by 1. And then the rest of the nodes get further away by 1, right? Because we move closer to our subtree, but then everything else gets further away by 1, everything that's not in our subtree. So the rest of those is 2 nodes. So 2 nodes get further away, so we add 2. And then we get 6 here. Yeah. And so that's how you can go from 8 to 6. And similarly, if we move from like 2 to 5 now, well, the answer for 2 was 6. So if we move from 2 to 5, we move to this subtree of just 5. So 1 node gets closer, so -1. And every other node gets further away, right? Like 3 gets further away from 5 than it is from 2 by 1. 4 gets 1 further away. 0 gets 1 further away, and 1 gets 1 further away. So as we go here, everything that's not in the subtree we're moving to gets further away. So we would add 5. And that's why we get 10. And then if you go from like 5 to 4, same kind of thing, and so on. So basically, to keep it simple, we're always going to just move down the tree, and then it's very easy to figure out, like, if we move from a parent to a subtree, what's the recurrence relation? It's just going to be everything in the subtree gets closer and everything else gets further by 1. And so all we really need is for every node, we need to know how many nodes are in its subtree, and we can do that recursively. So like, for example, here we know, okay, this is 6 nodes, this is 1 node, this is 4 nodes, 1, 1, 1. And then from there, we can figure out how many other total nodes there are because we have this n number, right? So if some nodes are in a subtree, then everything else gets further away. And we need to know what's the distance from all nodes to the root. And then from there, we can recurse and get everything else. So essentially what we're going to do is we're going to run 2 traversals. The first traversal will give us the number of nodes in every subtree, which is pretty easy. And I'll show you how to do that. And at the same time, we will also get this total from the root. And then our second traversal, once we have that, will just start at the root, and it will fill in it will recurse in every direction. And then from our current distance, we can calculate our distance to the places we're recurring, just because we know how many nodes are in that subtree. So we're going to fill out the actual distances in the second traversal. So hopefully that makes sense, and it should make a lot more sense in the code. So let's code it. So we can make some class variables to make this easier, so we don't have to pass them down. So I think I'll probably do that. So I'll probably make a tree as a class variable, and then a counts as a class variable, and a distances as a class variable, because that way I don't have to pass them to every single function. So we'll say map, and this is going to be, so this is just like making a normal graph from edges. So this can be either, so it'll be int to either set or list. I'll just do a list. And this will be the tree. And then we're gonna also have a counts array, which is just for every single number in n. We need to know how big n is, so we're not going to initialize it right away. But for every single number in n, we're going to say how many nodes are in its subtree. So we can say like int array counts here, and then int array distances. So these are the 2 we need, which will be like what we'll be returning. And I think that's it. We can also make an integer like n, which will just be equal to this n, so we can pass that down. I think that's it. Well, yeah. So because I don't want to just call a function with 50 different inputs. So once we have this, then we can say like n equals n, counts equals new int array of length n, distances equals new int array of length n. And now let's make our tree. So tree equals new array list. And then, so let's start off by filling out the tree. Yeah, actually it shouldn't be an array, this should be a hash map. So let's start off by filling out the tree from the edges. It's just like building a graph, basic building a graph. So we can say like for int array edge and edges. Let's get both things. So we'll say like x equals edge 0 and y equals edge 1. And then we can say tree, let's see which one we need. We need this one. So if x doesn't exist, let's make a new array list here for the children. Yeah, make a new array list for the children. And then same thing for y. So then let's add x to y as children and y to x children, because it's a tree, you can go in either direction. It's not like a directed graph. So we can say tree get x add y, tree add y get x. So now we can write a, or get, rather, wrong way. Okay. So now what we need to do is we need to write our first traversal function, which is going to traverse the tree and is going to update this counts array for every single node, and it will also return the distances from every node to the root. And we can do that in like one traversal. So let's write that. So we can say private, we'll return an int, which will be the distances from all the nodes to the root, int, and then we can call this like get counts or something, because essentially this is going to fill out for every single node how many nodes are in its subtree. So this will be int node. And we also need to make sure, so because this is not like a tree, it's an actual graph, you want to traverse down from the root to the children, but you don't want to traverse back up. So it's pretty easy to do because we know the root is 0. So we can just keep track of the parent, and then we're going to go through all of the children that aren't the parent. That way we're not going to like go back and have a loop. So we can say int parent. Yeah, and then we can have like a result distance that we're going to return. So it'll be 0. Yeah, and then we're going to say for int child and so every single one of these nodes is guaranteed to be in our tree because a tree, every node's connected. So every node will have at least one connection. So it's not going to be like not in the tree ever. So this is going to be just a tree get node. So for every child, if the child is not the parent, right? Because we don't want to like go back to the parent. So if the child is not the parent, then what we want to do is we want to recurse there and then actually get its like distance from the root. And the way this is going to work is like, let's say we recurse down to this node. So this node is going to return us 0. And so this will be 0, 0, 0 as far as like distance. Yeah, it'll return to us 0. And so when we want to figure out, like recursively anyway, because essentially what we want is we want the distance from the node to, or we want the distance from a node's children to itself. So like these two nodes and these nodes don't have any children. So the total distance of all the children of the node to the node for all nodes that are leaves is 0. And then for this node, what we need to do is we need to say, okay, for every single child, the total distance of every single child and its subtree to this node is however many nodes there are in here, right? So if there's only one, plus the total distance of all the children of the actual node to itself. And I'll kind of like update this as we go. So maybe I can just draw it over here actually to make it easier to understand. So let's see, so let's get rid of this. Make it look just like this and like this. Okay, so this will be like 1, 0, 2, 2, 3, 4. Then we need one more node, I guess. So let's just do something like this. I wonder if I can turn it. Okay, nice. There we go. Okay, so essentially all of these nodes, the distance of all the children to the root here is 0, right? So this is like 0. Oops. Oh, let's do this color. So 0, 0, 0, and then the number of nodes in the subtree is going to be all in 1. So in here, every time we return from a child, the distance that the child adds is going to be this number here plus the actual nodes in the subtree. Because if this was one big subtree, every single one of these nodes is now one farther away from this node as it was from here. So that's why we need to know the subtree. Yeah, so let's look at that. So basically we're going to say distance plus equals. So this is going to be the thing that the recursion returns. So get counts. So now the new node will be the child, and then the parent will be the node. So it'll be this plus the actual like how many nodes are in that subtree. So hopefully that makes sense. The distance from all of the children of the actual node we went down to that node plus this whole subtree, the number of nodes, because all of these are now one further away from this than they were from that. Yeah, so this is going to be that plus, and this should be counts of child, essentially the length of the subtree there. Yeah, and this will recurse first and then get this. So we're going to fill out the counts of the children. Like as we go to the child, we'll fill it out, then we'll recurse out, and then we can use that value. Yeah. And then what we need to do is we also need to actually add however many children there are into this whole thing. So as we're trying to figure out like how many nodes are in this subtree, every time we go down to a child, we're going to fill out its number of nodes, and then we're going to add that to this. So this will be like 1, 1, 1 added to this. And then finally, we also add 1 at the end to account for the node itself. So this will be counts node plus equals counts child. And finally, at the end of the loop, we add 1 more because we need to account the node itself. So the counts now will tell us for every single node we'll have however many children in subtree. So essentially what that's going to look like recursively is these will all return 0, but they will have 1 node in their subtree. Now this node will have 4 in its subtree because it'll be 1, 1, 4. And the total distance from everything to this node will be the sum of all these, which is all 0, plus however many nodes there were. So there were 3 total. So the total distance here is going to be 3. So it'll be like this. Then when we recurse here, this is the same thing. So the total distance here will be 0. And then the number of nodes is 1. And so now here, the total distance is 0 plus the actual node. So this will be 1. And then here, it's going to be 4. So it'll be 1 plus 4 plus... actually, no. So the total distance, this won't be 4. This will be 3, right? 3 is the total distance from everything to here. So it'll be 3 plus the number of nodes in here, which will be 4. So that's why you get 8. And the total number of nodes here will be this whole tree, so that'll be 6. So, and I think it'll be a little bit easier to see in the code. So basically, you increment the distance, then you increment the counts, then you increment the counts of the node here at the end for that one node, and now finally we return. So this distance is like the total distance from all the children to the node. So distance. And now we need to call this function, and this will be distance is 0. So this will be the distance of every node to the root. So distance is 0 equals get counts of the root, so 0, and then the parent. We just have to make sure that like the root doesn't have a parent, so we can throw in anything here. We can do like -1 or something. It doesn't really matter. And so that's one function. So now that we have that, now we can basically fill out the rest, because for every node now we have a number of nodes in its subtree, and we know how many nodes, like what's the total distance to the root. So now essentially what we're going to do here is we're going to say, okay, this distance is 8. So whenever we recurse, we are going to subtract the number of nodes in the subtree we're recursing to, and we're going to add the number of nodes that are not in its subtree. And that's basically that. So now, because we know how many nodes are total, so we have to write one more recursive function here. It'll be very similar to this, so we can copy this thing. So this will maybe like get distances or something. Oops. Okay, we don't need this anymore. This will just be void. We're just going to be filling out our distances array. So same thing. So essentially, we know that the distance. So if we recurse to a child, we know that distance distances child will be distance's parent, or distance's node, minus the number of nodes in the subtree we're recursing to, right? So like if we're going from here to here, all of these nodes get closer by 1, and everything else gets further by 1. So this will be minus counts child plus, and so we need to know, we need to pass down one more variable in here, which we have n. That's why I had it here. So this is basically going to be all the nodes, n, minus this counts child, because that's how many nodes are getting further away. And now we just need to recurse. So we can just say get distances child, and the parent will be the node. And then when we go to the child, when we're trying to look up its children, we'll use its value, which we already filled out. So you're doing like a pre-order traversal. So you don't need any of this. You don't need any of this. And now we just need to call this function as well. So you can just say get distances So this should start at the root, so 0, and same thing, parent. You can do -1. And now our distances will be filled out, so we can return distances. Oh yeah, so there is one other edge case here. So in here, you can have one node. So if you have one node, you'll have 0 edges, and then like you'll try to access edges. So we can just return early. So we can say like if n equals 1, then you have one node which has no distance to anything else because you're just one node. This is if. Then we'll just return a new int array, and it'll just be 0 because it'll be one node, no edges. So I think that's the case that's breaking. Otherwise, like you're gonna try to access edges that don't exist and do all kinds of stuff that doesn't exist. So, yeah. So hopefully this was pretty clear. The main thing to take away is, yeah, once you have a distance of like from the root, and you recognize like moving from the root to another node, I'm getting closer to all of the nodes I'm moving to, and then every other node is getting one further away. So instead of like recalculating, I can take what I had, and all I need to know is how many nodes are in each subtree, and then I can figure that out. So yeah, so now we have a definitely kind of a harder tree problem. I think most of these graphs where it's not like binary tree and it's like n-ary tree where you have like infinite children, most of these problems are definitely harder. I think binary tree and BST like problems are some of the easiest, even like the hard ones for that. So anyway, this is going to be O of n, because essentially we're visiting every single node once, and then we're visiting every single node once again. So we're kind of like running a DFS twice. So O of n time and space. So for every node, we had to write down how many nodes are in its subtree, right? This counts. So that's O of n. And then distances doesn't count, but because we have to do that, that's O of n. And obviously the actual recursive call stack also is O of n if you just have like a tree that keeps going like one level down. Or not one level down, like every node only has like one child and it's just completely linear or something like that. But yeah, definitely kind of a tough problem, I think, but you should get the intuition reasonably easily that you can go from one node to another node, like what happens. And I think it is easier to see with this like ruler thing. Like this is in a lot of problems that you can recognize that as you move, you get closer to some things and you get further from other things. So you can just do that all, like as long as you know how many things you're getting closer to and how many things you're getting further away from, you're getting closer to them by the same distance that you're getting further away from other stuff. So as long as you have the counts, you can do that. And yeah, it's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.